the density of, as you see here, let me show you here with the camera, you can see it here. Those are different steel, can you see it? You can see it here? Can you see it or you can't? So here it is, you can see it. Those are balls here. They are made of steel, used for bearings. So, and then we have to measure using verniers. A tool to measure the diameter. We need what? The diameter. So we have to determine their density. And then I found the density in the inside the literature, and then we'll make what? Percentage error. This time is not in the procedure to tell you to do percentage error, but to compare it. But we will be able to compare today this one here. You will have 4. In the past we had 5, but you have 4 of those, correct? And we will determine their densities, and then put this one here in Excel sheet, and then from there we can get the slope of this linear relationship between mass and volume to get the density, correct? But before that, we have to train ourselves to go to start, of course, with the procedure itself. So here it is, the procedure here. Let me just check my palm here. Okay, so this is, you tell me now how much does it read in the first figure here. How much does it read for those objects, the green objects here? Can I make it bigger? Want to see it bigger? Let's make it bigger here. So how much this the first one does it read in centimeter? You have to put this one here in the procedure. How much is measuring it? So from the ruler here. So it stops here, correct? So it stops here. So how much is read? You can tell me. 37 is 37, correct? And what? Point what? 7. And the units, you don't have to write it already in centimeter, correct? So you come to the second one. The second one is here. Is how much? Is, you can see 64. How much is it? 64 point what? 64.1. Okay, how about the eraser here? Take this one out. How much is this one here?
1.6.
So this is your 0 here. Start from here. This is your 0 up to here, correct? So with the help of the ruler, you can pinpoint where the point is. It's of all courses 5, correct? 5 point, and then you can count each subdivision is 0.1, correct? 5.1, 2, 3, 4, 5, 6, 7. Yeah, I would say 8. And this is the unit in centimeter, correct, guys? So this is the first procedure, and then you can take the snapshot. I'm not taking the snapshot. We know how to do it, correct? Take the snapshot. Snipping tool is there in the Windows. Snip the whole those 3 items we did in a blank Microsoft Office, in a blank one. Snip it out. Snip them out. So we have the results of all those 3. So snip the results out. You can do it one at a time if you want. So it will be easier. So do first one, and you do the first one here, and you do the second one. First one, take the snapshot of it. Second one, take snapshot with the third one, and so on. Any questions so far? That's straightforward, correct? Using ruler in your lab drawer, that's your the blue ruler. There's a color, it has blue. We have for you, they're in the back. They are in the back as well. So those are in your here, the blue ruler here. you use it to measure the width, the length, and the height of rectangular solid. So here it is. This is a rectangular solid. I will look into it. This is my, look at this. This is my length. This is my height, up. And my z-axis is x-axis. There, here is y-axis, is my depth or width. Depth or width. So, y-axis deep inside, depth. Up, that's z-axis. This way, the flat one, this way, length, x-axis. So, the volume has to have three axes. Three dimensions. Area has only two dimensions, y and x. There is no z. When I measure the area, correct, I measure just the, in this case, I will measure z and x, the area of this face. Not the volume of the whole object, but the face, for example. Correct? So you'll measure this one here in centimeter, and this ruler, if you look, it has two scales. The small scale is the centimeter we are interested in. So if you look at this scale here, the smaller one we'll be using, that's the centimeter. The larger scale is the inches, and we will not be using in inches, correct? And you know the relationship between inch and centimeters. 1 inch is 2.54 centimeter. 2.54 centimeter is a 1 inch. So, what's that? What's that? In the back of it, what it says? Where is it?
What are these?
No, not this. We are using this one.
Oh.
Yeah, this one, up front, not in the back. We're using up front here. We have two scales. The inches in the top, correct? The inches are in the, I think the inches in the top, larger, and the smaller is the centimeters. And the centimeters themselves are divided in 10 pieces. In what? 10 pieces, each one is millimeter. A centimeter is 10 millimeter, correct? 10 of those subdivisions are 1 centimeter. Each subdivision, small tiny one, is 1 millimeter. So 10 of these subdivisions are 10 of those are 1 centimeter. Make sense? So the dimensions is, this way is your x-axis, that's your length. Higher up, that's your z-axis. Deep inside, that's your y-axis. Correct? That's the depth or the width. So you write those here, and try to get at least some sig figs with the decimal. Don't let me like you get 2. Don't write it 2. We need to see how uncertain we are. So we'll be 2.0. If you get 2, write 2.0. 2.0. So the 0 will reflect the uncertainty in the value itself. Are you following me? So we have to have this decimals. Yes.
We need a total of 3 sig figs?
No, whatever is, I can't say, because you have to measure, because each object is differently. One object will give you 2 sig figs, one object will give you 3. I don't know. It depends on the object dimensions. So you can't tell up front. You have to measure it and see how much. Is it like, I don't know, from 0 to, that's the length here. Let's see the length here. Let's see the length. The length is, for example, this object here is 7.5. Yeah, 7.6. 7.6. So I will write 7.60. 7.6. I will add 0. The more sig figs you have, the better your precision, your precise. If you want to measure it twice or 3 times, you can see how redundant your values are. Yes.
So it's better to have 3 sig figs than 2.
Yes, better if you have 3. That would be better. Yeah. The more sig figs you have, the best your precision is. If you have just one significant figure, your values are not precise. Yeah, because if you repeat this experiment twice, 3 times, 4 times, then you can see how precise you are in this measurement. So that's the first. After measuring those theoretical drawings there, this is the following. This is the experimental one, correct? That's number 1. Come here and then we'll do the theoretical graduated cylinder. We have 3 of those. How many? We have 3. So how much is the first one? Well, sometimes it's very hard for me to see, correct? Are you following me here? So what I will do here, I will try to expand this one as much as I can. First, one at a time, okay? Then as I want to see the first one. Now I can, much easier I can see. I bring this one back to the original size, but I make it bigger because I want to see where the meniscus is. It's very hard for me to determine where the meniscus is, where the small tiny drawing is. So the meniscus will be somewhere. I can't even, I have to draw it. So it's what, 3.9 I will say. 3.9, that's very accurate. At the bottom of the meniscus, I can't, it's just, the pen is not. So it's 3.9. 3.9, I will add graduate cylinder. Listen guys, graduate cylinder and burettes. For the precise trials, it reads all the time 3 digits after the decimal. 3 how many? 3 digits after the decimal. 3.90. So 3.90. If it's in between I'll put 39.5. If I don't know 3.913, I'll put 3.95. But this is 3.9, correct? So let me take this one out. So this is 3.9. So now the question is, the next question is, I have to put how much is each subdivision. How much is this? How much is this, all those, how much they are? How much they are? Point what? 1. So each subdivision is 0.1 milliliter. So remember, that's volume, this milliliter. So that's the first one. Correct, guys? Let's take the second one. Let's take what? The second one. So I'm taking them higher, so well, it looks like I will lose this one. Let's take this one here, take snapshot of it if you want, and then let's go for the second one. I'm just deleting this one here, go for the second one. The second one, how much it reads? 400, how much?
60.
This is 400, correct? Each one is, how much is it?
10.
Each one is 10. Each one is 10. Correct? Each subdivision is 10. So 50, 60, 460. Well, to have a precise reading of a graduate cylinder, you have to read 2 digits after the decimal. Burettes and a graduate cylinder will have to have 2 digits. So I will write what? 00. 460 and then put 2 digits after the decimal as zeros. Are you following me here? So, and the unit is in milliliter. And the whole subdivision is what? 10.00 ml. Each subdivision is this one here. Let's take the third one. Any question about this, guys? Straightforward?
Yes.
Straightforward? Okay, let's take this one out. Can I take it out? Let's take this one out and look at the third one. This one is not large amount. This is how much is it? So we can say this is 10, correct? Each one is how much? 1.00 milliliter. Each subdivision is 1. This is 10, correct? 11, 12, 13. Looks to me 13.00 mLs. So the volume is 13 and each subdivision is worth 1 mil, correct? You'll come here after recording this. Of course, you will go back to your original. So that's how we can make it original here. So you can write all the stuff here. Size of the cylinder. The cylinder reads how much, the first one? 5 mils. Here it is. Size of the cylinder here, this is 5 mils. This is 500 mils, this is 50 mils. That's the size here, correct? So those are the sizes. You can come here and write those sizes here. You have, and that's a mistake here, guys. Can I take this one out? I have to copy because we have 3, but it's given to us 2. So what I will do, copy and paste this one here, if I can, if you allow me. It looks like it does not allow me because it does not have, I took the Microsoft Word, but anyway, so I have to shoot Microsoft Word, not the PDF. This is a PDF, looks to me. So it's not really opening. Yeah, it's not opening this. But anyway, so you have to copy and paste this one here. Copy it and paste it and add another row, another table here. Graduate cylinder number 3. Graduate cylinder number what? 3. You have to add it here, guys. There's 3 graduate cylinder, not 1, 3, correct? The third one you have to add it here. I by mistake opened not the Microsoft Word. Yeah, this I think it's the PDF. Yeah, so a PDF, so I can't write on the PDF unless I have a PDF writer. I have to have a PDF writer. So add this and then do the whole thing we did now. The smallest subdivision, the whole graduate cylinder, and the value of the liquid inside the graduate cylinder. Now, what this is the theoretical. Now we'll come and make out of this. I hope we can get docs. Let me see. We can get the docs here. Well, I can't get the docs. I have to convert this one to docs in my computer. The other this one does not have what?
You have it in there in docs.
Yeah, but it's not want to open in docs here. I'm trying to save it, but it does not want to open. Yeah, download. I did.
You have it's in the iCollege. You have it in there as
Where is it?
It's the middle one from the bottom. But down from the bottom.
Here? Here it is. I put it yesterday. That's I forgot I put this one down. Okay, guys, here it is. That's much better. So we have a slider here, a ruler, then make it bigger. So we did, I think, all this one here, guys. So now we have to add. We have 3 graduate cylinders. That's the theoretical one. So copy. Thank you very much for mentioning that. I forgot that I put it yesterday because you cannot write. So we'll add to this one here. Let me just add. Okay, I don't know why. Okay, so if it's not acting this way here, it's not even wants to. Well, listen, guys, it's not acting here, but I will do it for you. So don't start doing this. I will add to you in my laptop, the university laptop. I have a lot of software to do, but the simplest way to do that is to anytime you have a problem writing or something because of the restriction of the format, You insert every time. What is? Oh, I did not enable the whole thing. Okay, good. Well, now it might be. So you can add a box, and then within the box, you can add the whatever you like. So now I think it will. So copy, and I'll just do it here. Okay, guys, we have 3 gases. That's the theoretical one, correct? Based. So this is cylinder number what? 3. Now, guys, that's 3. That's from the whatever you have. Now we have here for you. I will say practical. Practical graduated cylinder. So it is practical reading of volume in a real graduate. So you will do here, guys, copy. I'll put this one for you guys. Copy. Okay, so copy, paste.
Oh, I thought it understood as
What?
number 2 we were going to do.
What's that?
Scroll up. I read that number 2, read and record the volumes of the 2 liquids present on display. I thought that was what we were going to do.
No, but the problem is graduate cylinder 1, which is this one here.
Okay.
Graduate cylinder 2 is this. Those are the theoretical one. I'll put this one. I did not write those lab reports. Somebody else, so I apologize. Somebody else had written them, but at least those are the 3 theoretical one. I will add to this. Read, record the volume of liquid in the theoretical graduated cylinder. So you can put this one here, guys. Highlight theoretical here. It is. Let's not want to highlight here. We can highlight this one here in blue, red. So, and okay, guys, correct. And then those are 3. Then we'll do not practical. Then we'll read the same thing here. We'll say copy, and then we'll paste everything here. Home and paste. So instead of theoretical here, we'll say practical graduate cylinder, guys. So that will be that's number 1, and we'll add to it okay, guys, here it is. And number 2. Let me just paste this one here. No, it is not going to take it. But let me copy and paste. Okay, guys, I'll put this one for you here. Now, this one here, guys, here, listen. This is graduate cylinder number 1. Copy it. And this one here is graduate cylinder number 2. Okay, guys, so here it is. I'll put this one here for you. So, what are those practical ones? Here, guys, can you see it? this is a dark green solution, but put in two different sizes of graduated cylinder. This is 100 mils, and this is 10 mils. One is 100 mil size graduate cylinder, and one is 10 mils of graduate cylinder. So those two, the solution in both are the same color. So we are not interested in the color, we are interested in the size of the graduate cylinder you are using, and we are interested in the whole volume and the subdivision. Okay, we are interested in what? In the subdivision. I'll send you this file there. So we are interested in the whole graduate cylinder size and the subdivision of each scale here, and the amount of the liquid inside. Do not try to open those. Do not open those. Keep them as they are, because otherwise they evaporate, and every time we will be losing some of this solution. Make sense, guys? Make sense? So we have two of those, 1 and 2. Everybody's following? Now, I know you cannot sometimes you cannot circle, if sometimes Microsoft will not allow you, but you can highlight your answer, and red and background, background will be yellow background, then will be that answer. So whatever this one here, for example, I can write, for example, this is the answer is here, so I will highlight this one here, write it in red. That will be my answer here. So my answer is, so here it is, and bold. Yeah, that's my answer. For example, just show you as an example here. That's an example. So if the insert of the shape, sometimes Microsoft is very hard, because all this formatting going on, it's very hard to circle. It will not allow you to put the shape in, but sometimes it does. But anyway, so you can highlight and put the same way I did. So we have two types of graduate cylinder. That's the volume. First, this one, the length. The first one here was the length, correct, guys? The first one you can see, that's our length. Then we went to the volume. The length is, we said, this is the theoretical length. And then we have to do the practical one, remember? This one here. Measure the draw line, and yeah, this the length is theoretical, this the length practical, correct? And this is the theoretical volume, this is the practical volume. Now, after measuring those two, now we are time to go and look into the mass. Everybody's following? May I have your attention here? Those masses, you don't have to weigh them. They are weighed for you. You need just to go and look at what? At the value there, correct? On the balance. So those are three top load ones. Which one is very expensive of all? Which one is very expensive of all? How many digits does it give us here? 4 digits. How many here? Maybe the mass of it 4, but this is 4. This one will give you 4 too. But this one here gives you what? 5. So this one here, expensive. And those are called top load balances. In the kitchen, you need something like this, cheaper ones, smaller, from Amazon or Walmart, whatever. Those are cheaper ones, correct? So now you can read how many significant one this one does it have? How many? 5. Sig figs. How many here? 3 sig figs. How many here? 4 sig figs. So you don't have to weigh, you have all the weighing for you done, correct? And that's what you have to do, just fill in, you'll fill in all those here, significant figure, all the numbers. Write the number, write the masses here, the masses is here, and then here is sig figs. Here the sig figs. Correct, guys? That's the mass. You don't have to wait. You just look at the picture and determine those masses. Any questions so far? Any question? Okay, that's good. Let's take this one out. Now, this math here, I want to go to the actual lab to measure the vernier and everything. But here it is. When you come to this, the answer has to be rounded to what? To how many digits after the decimal? Don't let me down now. Don't let me down. So how many digits we are adding? Correct? Addition. The rule, if I add of significant figure, I go by the least digit after the decimal. Least digit, addition and subtraction. And subtraction. And this is least digit after decimal. Correct, guys? So now let's look at this. How many? Well, this is from the calculator here, correct? So how many digits after decimal? One digit after decimal, correct? Why is one digit? Look at this. This is one digit. This is 3 digit. This is 2 digits. The least one is what? It's 1 digit. So you have 1 digit. So you come here when it comes to the multiplication and division. This is multiplication. And the same thing rules and division here. The same rules here will be different from addition and subtraction. Here the least digit, the least significant figure. Here least sig figs. So here is 4. Here is 2. Here is 3. So your answer has to have how many? 2 sig figs. Rounded to how many? 2 sig figs. That's the least significant figures. Everybody's following?
So we go with the least?
Here multiplication, you got the least significant figure. If you add or subtract, the least digit after the decimal. Correct, guys? And the same thing here will be how many? This is 3, this is 4, this is 2. So you have 2. Correct? However, this one here, how many? You have 3 digits, 2 digits, 2 digits will be, in this one here will be 2 digits, not sig figs. 2 sig figs here, and here 2 digits. So depending what you are doing, then you can do this one here yourself. Okay, guys? Okay, so how about the other ones before we leave this one here? So you can do this one here at home, not doing it because we want to finish reading those and the balls here, the stainless steel. So now how many here is what we have here? Tell me what we have here. 5, number 5. Number 5. Number 5, guys. How many? 2 digits, and here 1 digit. No, 1 digit, not 2. Why 2? You are adding here, guys. You are adding. You are what? This is addition. You are adding. And if you add, you go by the digits after the decimal. Here is 1. And here is how much? Is 2. The least one is 1. Come on, guys. Don't let me down. Don't let me down. That's in the lecture, though. Whoever in my lecture, we'll cover this one here. Let's go here. So let's go the other one, the last one. This is what? Multiplication. I go by what? Sig figs. So how many sig figs I have there rounded out to? How many? 3. This is 3 sig figs. This is 4 sig figs. My answer has to be rounded to 3 sig figs. Here is sig figs. Here, 2 digits. So, even your answer, 2 digits versus 3 sig figs. Digits if you have addition or subtraction, and the other one is whenever you have division and multiplication. So, okay guys, any questions so far? Any questions so far? Okay, let's take this one down, and let's go down, down, down. Here we will do conversions. Now you can, as I said in the quiz or the exam, print yourself a chart. Print yourself a chart of this conversion between metric English, and so on, or metric SI. So here is it give you some small tiny tables. The relationship between metric within metric English. So here it is. If I go here, I have, look at this guys. Here I have English to metric, correct? And here just metric to metric here, and here again is metric to metric. And this is not, the time is the same with the English, or the time is always the same, but this is mostly ml, milliliter, and so. And an example here give you 1 kilogram is 2.20 a pound, correct? So ask you, so that's the relationship how you can do this, the setup, your setup of the conversion, correct? So I wanted to do this one here at home. We went through that in the, if you are in my lecture, we went through that in the lecture. If you need any help in those conversions, ask me, and I'll be more happy to have a meeting with you in WebEx. We can go over this metric English metric, SI metric, whatever you like. So that's the units here. Any question about this, guys? Please, any question? Any question about these conversions? Any question about these conversions? Now this decigram, centigram, milligram, kilogram, and gram. Well, it turns out to be, always watch out for these prefixes. D stand for 10 minus 1, C 10 minus 2, M milli 10 minus 3, and kilo, small k, is 10 plus 3. So you have to know what the exponent you are dealing with for the conversion sake. So in order to have conversion done correctly, you have to know the powers, the exponent value, those prefixes you have to know, deci, centi, milli, kilo, and so on. And we have, even in the lecture, more. We have tera, we have mega, we have the lower one, pico, nano, and so on. So, okay guys, I'm not spending time on this. I'm going to the last topic. Unless you need help with this, you can come and see me, please. I'm not spending. So now look at this. I want to solve this one here. 23.7 meters. How many are in centimeters? Somebody knows how to do it? Somebody knows how to do it? Okay, I trust you. You know how to do it. I can show you one method here. I showed my students, easy, and then you can do the other one. What you like? I will do 1, 2, and 3. Bless you. So tell me which one you like. 1, and 3, and 4. Which one you like? Which one you like, guys? Come on, guys. What's that? Number 4? Okay. One of the world's heaviest men weighed 413 kilogram. How many pounds is that? It's given to us what? So it's given us 1 kilogram is 2.200. So it's, they have written what? They have written the decimal Not in the top, there was just 1. I have always to introduce the decimal because of the precision. So, well, what we have to do, we started with whatever is given to us. We need this one here in pounds, correct? So pounds we don't know. It's always whatever given to us. Kilogram, correct? I have to go through the basic unit, which is 1 gram, and it's equal to 1 gram. 1 gram is not 1 gram. Sorry, 1 gram and kilogram at the bottom. Kilogram at the bottom. Bless you, kilogram. Okay, guys. I showed my students always the trick here. Let's look at this, guys. I'm looking at the. Let me just go up here. Okay, guys, here it is. Okay, guys, so I have here a kilogram, correct? Kilo is 10 power plus 3. 10 plus 3, correct? So I have to put something in front which is opposite to that exponent value. I'll put 10 minus 3. Why? Because 10, this is, K is 10 plus 3. 10 plus 3 multiplied by 10 minus 3, the factor I have introduced, is 10 power 0, which is 1. So the whole value here is really 1. Just I added the opposite of it, 10 kilogram, correct? 10 minus 3 kilogram is 1 gram. And then I take the basic unit 1 gram, correct? So I want to kilogram to kilogram with the kilogram cancels out. I need 1 gram, correct? Or I can't do this one. Maybe I did further one unit. So let me back out here a little bit. I'll show you. Let me back out and then show you a little bit. Let me see. I don't know why it's not moving, but anyway, so this is wrong here. 1 pound, question mark. I don't have to go further. Kilogram, and then just kilogram at the bottom and pound in the top. So 1.00 kilogram is 2.20 pound. Kilogram cancels out. You have 4 sig figs, you have 3 sig figs. The answer will be in 3 sig figs. Correct, guys? So let me, I don't know what's happened to this now. It's not moving anywhere. And now it's moving. Okay, good. So let me take this one out. And you know how to do it, correct? You know how to do it, guys? So what I did with this is just straightforward. But this is 4132 kilogram over 1 kilogram at the bottom, 1.00, and this is 2.20 pounds. So kilogram to kilogram cancels out, and your answer will be rounded to 3 sig figs. Now, what I wanted to show you here is the other one. The other one here. Let's take here, guys. I need to know one of these, 2 or 3. Let's take the kilogram. We did the math. Let's take this one here. Let's take this one here, guys. So what I'm doing here, I need centimeter out meters. okay, or I need centimeter of kilo, whatever. I can do that. Let's do this one here. Maybe the kilo with this. So I start with how many centigrams is 0.488 kilogram. I have to go to the basic unit. 1 gram is 1 gram is kilogram here, correct? Which is 10 minus 3 kilogram. Why? This is 10 plus 3. I put in front of it, so you'll equalize the 1 here. So then multiply by, I need a centimeter, correct? Centimeter grams. So kilogram with kilo cancels. 1 gram, here is centigram. Centigram is 10 minus 2. I'll put in front of it what? 10 plus 2. So the whole question is this one here, 0.488 kilogram cancels out over 1, and this is 1 gram, and this is 10 minus 3, correct? And this is 10 plus 2, CG. Okay guys, so anytime I have the prefix value exponent, I have to swap the sign of it. Kilo is 10 plus 3, correct? So I put in front of kilo here, guys. In front of kilo, I put 10 minus 3. The opposite of the exponent 10 plus 3. In front of the centi here, 10 minus 2, I put what? 10 plus 2. Correct, guys? Everybody is following? That's easy way to get of the units. So now, this grams out already with the gram here. Correct? So centigram is left here. So then I take this one here up. I have to change the exponent because it's underneath. So it will be then, the whole thing here will be 0.488 multiplied by 10 plus 3, because I took it from the bottom up, plus 2 CG. So this is 0.488 10 power plus 5 CG. That's the answer here. So whoever in my lecture, we went through this for two lectures. We spent time on this, how to convert within metric to metric. That's the very difficult, confusing for the students. And anytime I have a prefix here, C or K prefixes in a metric system, I have to put the opposite value of that exponent. If it's positive 3, I have to put minus 3. If it's a negative 2 centi here, I have to put in front of it a positive 2. It is centi is 10 minus 2, I put in front of it the opposite of it, 10 plus 2. Everybody's following? We did this one here in the lecture, whoever in my lecture. So if you feel that you need help with this, just let me know. I'll be more than happy to cover this one here. So, any questions so far? Okay, so let's, you can do the rest of those. Do please all of them here, so you get the idea how to do them. If you have still confusion how to do those, let me know. Please let me know. So now is the last one here. Well, the last one we have to measure all those 4, correct? All those 4 different sizes. Different sizes means different what? Masses. So first of all, you take one at a time and measure their masses. So measure their mass, all of those 4. You will not be confused. So take whatever from the smallest to the highest diameter, correct? So we will do the measurement of the density of those 4 different pores. So the idea is to take the density here. Somebody had covered this one in the lecture. We covered this one in the lecture already. Density is what? Density is what? Ratio between mass over the volume, and you have to give the temperature here, which is here is I think if you look at the thermometer there is about, I think it's, I feel 22 degrees, not 20, not 25. So mass, you get the mass of those four, correct? Mass of those four. Now you have to use the vernier to measure the what? To measure, you'll be using inside this flat beds here, those flat beds inside, not out, but the flat beds. You put them there and you snag the whole thing here, and then you read not the top one, the top 1 inches, you read the bottom one. The top 1 inches we put the centimeter, correct? So you read how many of this. So this is a little bit not tricky, but you have to do some calculation sometimes if you get a fraction of this. So the mass is direct weighing, correct? You use analytical balance with the boxes, analytical balance to weigh the masses of each of those boards, correct? And then the volume of this is what? Those are spheres, correct? And everybody knows how to get the volume of the sphere? The volume of the sphere. You need the volume because mass over the volume. So this is, was that for what?
4/3 pi r cubed.
That's correct. So so it looks at this one here, and before we are doing this, I'll show you how I'm sure this, but I have to show the movie here a little bit for 1 minute. How to use this vernier is a little bit trickier, but very very precise. Not accurate, but I would say very precise. Accurate if I know the value in advance, I would say accuracy. But I don't know the value of them. I don't know the mass or the diameter. I don't know. We are measuring the diameter, so the radius cube is diameter is twice the radius, correct? So here it is. That's explanation is not really very good explained. But let me. I hope it will play within the video here.
I will work with a vernier caliper. The way this works is that there is again an upper and lower scale. Here, this is the centimeters 0, 1, 2, 3 on this axis here. And then on the upper we have inches, which we're going to neglect for our use. And then this is the lower scale down here, 0, 1, 2, 3 up to 9. And then 0 again is the minor scale. When it's shut, the vernier caliper isn't measuring anything that is, then the zeros on the major and minor axes line up. So we can see that this 0 on the minor scale and this on the major scale, they line up quite well. And you'll notice nowhere else does it occur, that is the markings on the minor and major scale line up, except again at 0 here and there. We'll put our measurement object here between the teeth of the vernier scale, and we'll close it. When we're measuring something, there's a flat side here, and we'll want to put our device in that, and then close it with a little bit of pressure. And with that value, we're going to see what the measurement is. On the major scale, it's the question of where does the 0 on the minor scale line up with the major scale. So here we have a 0 on the minor scale, which is a little past this hash mark here. So that's 5, 6, 7. It's a little more than 0.7 centimeters. The question is, how much more than 0.7 centimeters is it? Since the 0 here doesn't line up with the major scale exactly, we need to find where on the minor scale it does. So there's no match here until we reach, say, the 6 value. So on the minor scale, the 6 mark lines up pretty well. You could even say the 7 mark lines up better. So we'll take this 7 as our minor scale measurement. Now the question is, how do we combine this 0.7 centimeter measurement on the major scale with the 7 mark on the minor scale? The answer to that is over on the far side of our caliper. There's a little marking that says 0.05 millimeters. This tells us the smallest unit of measurement for the caliper. So now when we look back, this 0 on the minor scale is somewhere between 0.7 and 0.8 on the major scale. So this gives us some confidence that our measure is correct. Now that we know the smallest unit of measure on the minor scale is 0.05 millimeters, that tells us what this 7 means. Each of these small marks from here to here is 0.05 millimeters, and so since this is 7, and then there are 2 marks per increment, there are actually 14 of these small measurements. The way we'll combine these sets of measurements, the 0.05 millimeters on the minor scale as the smallest measurement with the major scale of 0.7 centimeters, is we'll take the major plus the number of minor increments, in this case 14, and then multiply that number times the smallest measure. So what we get back after we convert to the correct units of centimeters, in this case, is 0.77 centimeters, with an accuracy of plus or minus 0.005 centimeters. As a check, this makes sense because the value should be between 0.7 centimeters and 0.8 centimeters. And if we look back at our original measurement, we see that our 0 mark on the minor scale is close to the 0.8. So 0.77 centimeters makes sense. Now, as an example of what happens if our scale is slightly different, if we're using a different measure, and we come up upon a case where the 0 on the minor scale lines up with an increment on the major scale. For instance, now I see that the 0 on the minor scale lines up very well with 1.7 on the major scale. What that does for our calculation is we still have a major scale of 1.7 centimeters, but now our minor measurement is 0 increments. And we multiply that times our smallest measure of 0.05 millimeters, and what we get back is a more precise measure of 1.70 plus or minus 0.005 centimeters.
Okay guys, that will give you the idea how to use. It's not really difficult. It's not really difficult. So if you have any question, come forward and see me. The main thing is in the density of those 4 balls, which we will do the Excel file for them to get the density from where? From the Excel file by graphing. So you have 4 different ones, 4 different masses versus 4 different diameters. The diameter is twice the radius. We are not interested in the diameters. We are interested in the radius of those spheres. Those are spheres, not circles. Circle is the area. The sphere is the volume, correct? So those are spheres, and we have to determine. Please do not drop them on the floor. If they are dropped in the floor, they might get cracked a little bit from the surface, and that will affect the diameter, your diameter measurement. So you might, so be careful. Just careful with dealing with those, so we don't need to lose the real diameter for them. So now with this one here, you will make an Excel file. You do it at home, and I have for you one that's Excel file. I hope I have it here. I have it. I think it's here. Let me see. Okay, this is one of the students. I think I gave you in the lab reports one, but I did not like the sphere data. These students came out with a very good data. So here it is. I'll put you this data as well. You can look into that. So here it is. We have the first one here. The students measured what? The students measured the diameter of. You start with the 0, of course. 0, 0, 0, 0. This is your coordinates. 0 coordinates. So, and then you have 4 balls here. That's the different diameter measurement with the vernier tool here. correct? So that's diameter here, and then what you will do here out of this one here, you can calculate how to do the mass here, correct? I'll make a lab report for this tonight. You'll like it. The way I'll put it away is very nice. So what's the relationship between? So you'll come here and then do all this stuff here together to determine what? To determine the radius by measurement and the weighing by measurement. However, when it comes to the density here, you have to so you have to do the density by calculation. You can do that by the by calculation of the volume of a sphere, correct? You can do the calculation of the surface area, correct? And you can get the volume of each sphere, correct? So you have 4/4 of the pi multiplied by r square, and you can determine what? You can determine the density, but you don't have to do the density. We'll do it through what? Through Excel. So you have the mass here. Let me come here. You have the mass. You measure the mass, we said, correct? So that's what you are measuring here. That's the mass here. 0, 0 is one part of this. That's the mass and that's diameter. Okay, guys? And then if you have a mass and diameter, you put the formula for that. The formula is given to you here. So the volume of a sphere is, correct, is 4/3 pi r cube. Now r cube, I don't know. I did not measure r cube. So I will do, instead of r, this one here, 4/3 by diameter over 2 cube. That's the volume of what? Of the sphere. I put it in a formula there. I'll put this one in a formula. So then I will know the volume here, then I will get all the volumes there, correct? That's I mean, not the volume, that's the volume of the sphere. Then I have the mass here. Each of those masses there, just transfer them. They transferred as they are here. See here? They transferred as they are. I measured, this is the diameter transferred as they are. Now I just do calculation, the radius. You can calculate the radius. The radius is d over 2. Here it is, that's the radius. Radius is diameter divided by 2. That's the radius here, guys. You have the 0, 0 base remain as is. Those are 4 radius, 4 different diameters here, correct? We're using vernier. And this is the masses using the balance, correct? Then you get the volume. This surface here is that's the volume here for each. You can get, this is the formula here you put, correct? And this is the volume here. This is the volume here. Now, at the end of this, you'll plot the mass is your y-axis, correct? And the volume is your x-axis to get the density. But you can train yourself to plot each node of, as they said in that's a practice. You can practice. That's what they say. So you can practice whatever they tell you. Take the value, take the surface area. You can plot anything you want. Diameter against mass. Diameter, mass against surface area to see the relationship. Now if you look at this, here it is. Those are the ones you will, after having this table here, after having this table in the Excel, you will have the relationship between mass and diameter. This one here and this one here. This is the curve here, correct? Second, Let's do the second one. The second one, you can have the mass, surface area against the mass. Okay, surface area, it is mass against surface area. All this from the table you have above. Remember the table? What you need today, you can do the whole thing at home, but I need you to measure what? Including the 0, 0, 0 coordinates, the diameter of 4 balls. You have 4 balls, diameter of them, and their masses. And the rest, Excel will do it for you. And then you will have to play mass against radius, mass against surface area, mass against volume. That will give you what? That will give you the density. Mass over the volume will give you the density. So here it is. Let me take this one here. So we played against 2 items here. We said first here it is mass against diameter, correct? From the table here at the top. From the table at the top. Correct? Mass over surface area. Mass over the volume, that's our goal here. That's what we're really very important. This is, and you get the linear relationship. Your y-axis is the mass. Your x-axis is your volume, and the slope is your what? Yes.
So for this lab report, the labeling is important now.
Yes, yes, mass here, and this is volume. It's very important. If you flip it, then the curve will be flipped. Instead of having this way, it will come this way. Negative value. Density is not negative value. The density is positive value. If you flip it, it will come the other way. Are you following me here?
Yes.
So,
The last lab report, it didn't matter if you labeled it. So
this one is very important because this one is a ratio of a real object. That one we don't know about. The first lab, we just having a couple data and we put them as we don't know what we are dealing with. Here we know that's what? That's stainless steel. Correct? And this one here, where you get the intercept and then intercept and the slope will give you, because density is mass over the volume, correct? And this is really, if you have this one here, will give you something like this. And the slope of this is the mass, this is the volume, and the slope is here, slope is your what? Is density. Slope is equal to what? Density. This student I liked by far a couple years ago. This one, the only one gave me a very good data, but I gave you the one has no data inside the whole thing. So look at this students here. Really, he did very, very well, and look at the data he got. So in the literature here, the value is this value in the literature. So here it is. The value here in the literature is that's what he got. He got I think he got I can put for you maybe different value here. Let me this is the slope is 8.16. Even his data will be much better. So this is the practical one, correct? 8 point, I'm reading this one here, 8.1651. So write with me this one here value. Now I want you to Google what's the density of steel bearing balls. So somebody will Google that. How much is it? How much is it? We can Google it together here. Let me Google this. Let me take this one here.
approximately 7.8 grams per cubic centimeter.
7.8. We can Google this together here, and then I'll say Google not Google Translate. So, what is the density of stainless steel bearing balls? So just quick, it's between 7.5 to 8.0, and AISI stainless steel ball, I don't know what type. That's the problem with what really steel is. Somebody will tell me what steel is. What steel? Metal, yeah, it's a metal. What type? What's stainless steel here? Why it says give you those two values? Why 7.5 by?
Iron will be oxidized.
No, this is iron and what? Carbon. Depending on the carbon, then the stainless steel will be hard or will be just soft. Correct? So I don't know what the brand of those are, so I don't know. There is no name on them, so they are like this. So therefore, that's the reason whenever you get this not exact values, that means this material is made of what? More than one element there. And therefore, you cannot tell, according to manufacturer, the manufacturer will tell you this is how much in each of those balls carbon, how much is iron inside. Iron is the majority. This is the major element inside. Element is iron, and then depending on the softness and hardness, then will be the carbon there. So, and I say I will take bearing steel balls. Let's look at this. Here it is, What is the density of stainless? I will take it as 7.8. Can you see the guys here? Here it is. 7.8. I will add zeros to make whatever I have. The intercept came out to be what? To be 4 digits after the decimal. I'll put 2 digits after the decimal. This is my theoretical value, guys. This is my what? Theoretical. This is by experiment. That's what I measured. Am I close enough? I would say yes. Let's do a percentage error. Somebody tell me what's the formula of percentage error? Theoretical minus experimental divided by the theoretical multiplied by 100, absolute value. So the theoretical is 7.80 minus 8.165, 0 over 7.80 theoretical absolute value multiplied by 100%. Correct? Everybody's following? That's you can please use this value here, and then intercept, whatever intercept you are getting out of this. Correct, guys? Whatever you are getting out of this. So 7.8, that's your theoretical value, and this is this is the theoretical from the literature here, and this is the experimental value. So he got out of this, he got 4%, which is I was really very impressed with his finding. Let me see here. Take this one down. Maybe. Let me take this one out. So here it is, and see if no, that's the procedure here. For some reasons, that's the density, but that's not his lab report. I don't know why it's taken out, but here it is. Let's get it there. So the student got out of this is if you look at this, that's his graph, which looks very good. I mean, if you look at the graph looks very good. Mass over the volume. Intercept is this. Theoretical by experimental 8.156. And here it is. He took the plus, but I take absolute value, and he got 4%. This is very good data, better than the other one. The other one did not deliver. So I will do for you this one tonight. I'll send it to you. Just concentrate yourself on finishing the first lab report, submit it. If the Dropbox is closed, let me know. I'll open for you, and then you can do. This is the percentage is just 4%, which is really very, very well done. The student done very good experiment. So you can see 4%, 4.0%, which is very good, excellent data. So what we have to do, the lab's almost done. 2 items, or yeah, 3 items. First of all, you measure this, 3 dimensions. Read those 2. Okay, whole volume of the liquid, and the small subdivisions, how much they are. Correct? Here the 3 dimensions. Correct? And the other ones are already inside. The theoretical ones are inside. And then here measure the mass of those 4, and measure the diameter using this. Correct? Any question? And I'll put for you those data here from these students, because I like the percentage error. He got 4%, which is really very good. Yes?
Are they going to be in the drawers, or are we going to use the
No, those have to be there inside. I'll put them inside as soon as we finish. I think we are done with the experiment. So as I said, 3 items we have to do in the lab. Just 3 items. The rest has to be done at home. Correct? The Excel file and everything, you can do it at home. So as I said, repeating myself, 3 dimensions of this rectangular. Correct?
Are those the only ones?
That's the only ones are given. No, balls we have plenty. So the mass and diameter of these spheres, correct? And the volume of those 2 graduate cylinders, 2 liquids here. We have 2 liquids. This is dimension of this the rectangular, and then this is the stainless steel bearing balls, diameter and the mass of them, and the Excel file used to determine the density and the percentage error. I want to see the percentage error. Okay, I'll stop.